So we come now to another one of those kind of stealth L'Hopital's rule forms. This one is 0 to the 0. Now you might ask, why is 0 to the 0 indeterminate? It certainly looks like it might be just 0. Um, Basically, think about two rules that you know about how exponents work. One is that you know that anything to the 0 should equal 1, but you also know that 0 to the anything equals 0. So which one of these rules turns out to be more important if we have if we have one expression is approaching 0, the base is approaching 0 and the exponent is also approaching 0? Which one of these is going to turn out to be the more important 0? We don't really know. So let's see an example like that. Let's evaluate. The limit as x approaches 0 from the positive side of x to the x. So here we have 0 to the 0. I should make the point, by the way, that L'Hopital's rule does work for one-sided limits. We've already seen one of those, and it works the same as it does for two-sided limits. So anyway, here clearly we have, if by substitution would give us 0 to the 0, so we do have a 0 to the 0 form. This is how you do this. What we're going to do is we're going to suppose that L is equal to the limit as x approaches 0 plus of x to the x. In that case, we can say that ln of L is equal to ln of the limit as x approaches 0 plus of x to the x. In other words, I just took the natural log of both sides. There's a rule that you've learned that the limit of a log is equal to the log of a limit. That's a special case of the composite limit rule. So I can write that ln L is equal to the limit as x approaches 0 plus of ln x to the x. This should start looking familiar, that we have this transformation that when we have a complicated exponent to deal with, we take its log and bring the exponent down as a factor. We essentially did this there were a couple of examples from earlier, particularly involving logarithmic differentiation, where we did this operation. So we're just doing it now in a different context. So this is going to be ln L is equal to the limit as x approaches 0 plus of, I bring down the x, and this is going to be x ln x. Now, we already evaluated this using L'Hopital's rule in a previous problem. We already saw elsewhere, using L'Hopital's rule, for this 0 times infinity form, that the limit as x approaches 0 plus of x ln x was equal to 0. So I'm not going to redo that or show you why 0 times infinity is L'Hopital's rule form. I'll just refer you back to that problem. The point is, we already know what this limit is. So we know that ln of L is equal to 0. And therefore, that means that e to the ln L, which is just L, must equal e to the 0, which is 1. So that means that we conclude by saying that the answer is 1. So here, I've actually just deferred to another use of L'Hopital's rule, but if I didn't already know what the limit of x times ln x was, I could have used L'Hopital's rule in the way that I did in a previous problem in order to find that it's 0. So this is fairly important operation for evaluating those indeterminate forms that involve exponents.